You have learned how to classify triangles as acute, obtuse, or right, as well as also equilateral, scalene, or isosceles. But how are angle and side lengths in a triangle actually related? Angle E in this triangle is obtuse, clearly, 120 degrees. Any triangle with angle E as a vertex is going to be an obtuse triangle. Our goal in this segment, we're going to learn how to examine the relationships between angles in a triangle and the classifications of the triangles.
Hey, so like obtuse triangles?
Well, yeah, they're triangles with one angle measuring greater than 90 degrees. One obtuse angle means you have an obtuse triangle.
See, but that's my question. Can you have a triangle with two obtuse angles?
I mean, that's a good question. I have no idea. Should we try drawing one?
Yeah, we could try that. Let's say we have these two sides of a triangle with angle BAC as the obtuse angle.
Now, let's try adding an obtuse angle to point B by drawing a line segment from B to D.
Well, we definitely have two obtuse angles now, but it is not a triangle.
Yeah, I mean, we already have three sides and the shape's not complete.
I guess that means it's impossible to draw a triangle with two obtuse angles because you'd need a fourth side.
So there's our answer. Mystery solved.
Take a look at angle PQR. Notice that this angle is an obtuse angle. So if I go ahead and then create any triangle with an obtuse angle, what do we notice? Well, first of all, that the measure of angle P plus the measure of angle Q plus the measure of angle R must sum up to be 180, because the sum of the three interior angles of a triangle is 180. What else do we notice? Well, as we noted, the measure of angle Q, this obtuse angle, that's greater than 90 degrees. Now think about this just for a second. If we know that the sum of the measures of the triangle must be 180, well, that means the sum of the remaining two angles, and that'd be angle P and angle R, their sum must therefore be less than 90 degrees. And so we can now generalize and say for any obtuse triangle, the sum of the two remaining angles that are not obtuse, they must be less than 90 degrees. You've been doing a really good job answering the question, how are angles and side lengths within a triangle related? What have we done? Well, we've been analyzing different types of triangles, and we've noticed that some triangles don't exist, like obtuse triangles with two obtuse angles. What are we going to do next? Well, we'll turn our attention to determining the side length parameters to see what types of triangles do and don't exist. The triangle inequality theorem. This states the sum of the lengths of any two sides of a triangle is going to be greater than the length of the third side. In other words, any two sides of a triangle must add to be larger than the third side. Now, for example, here is side C. It is going to be smaller than the sum of the lengths of A and B. And here is side B, right here. It is going to be smaller than the sum of the lengths of sides A and C. And right here, side A, it is going to be smaller than the sum of the sides B and C. Well, a different way of thinking about this theorem is that each possible pair of the two sides must subtract to be smaller than the third side. In other words, it's not far-fetched to take this inequality and think about it a little different, that C minus A must be less than B. Or C minus B must be less than A. And we can do this with any of the three inequalities. We can say that B minus A must be less than C, or B minus C must be less than A. Going to the third inequality, and again, rewriting it, we can say A minus B must be less than C, or what? Or A minus C must be less than B. Notice the inequality at the bottom of the screen. What it says is that if you take the difference of two sides, this will be less than the third side, which will be less than the sum of those two sides. For example, suppose we had A to be equal to 10 and B is 4. Now the third side is C, isn't it? So this inequality says that A minus B, or 10 minus 4, must be less than the third side C, which must be less than the sum of the two sides. Well, that would be less than 10 plus 4. In other words, we would say that 6 would be less than C would be less than 14. In other words, side C would be between 6 and 14 units. This is a strict inequality because there is no or equal to underneath the symbols. Given a triangle, what we want to prove is that the sum of the lengths of any two legs is greater than the third leg of the triangle. Given triangle ABC, I want to prove that if I sum up lengths AB and AC, that'll be longer than the length of the third side, BC. Now, how do I do this? Well, the very first thing I'm going to do is I'm going to draw a perpendicular line segment from vertex A to segment BC. So there's my perpendicular line segment, and I'm going to label that point of intersection E. Now, what we know quite specifically is that if I go through point B to line segment AE, the shortest possible distance will be that line that connects the point to the line segment with a perpendicular line segment. Well, that means BE is the shortest line segment that goes from B to AE. Now let's think about this. Do you see another line on this diagram that goes through B and connects AE? Now, I do. That's AB. And because BE is the shortest distance that will connect B to AE, AB has to be greater than it. That's what we're saying here, that BA is greater than BE. Don't lose that thought, because all I'm going to do is say, let's pick another point, and the other point we're going to pick, ladies and gentlemen, is point C, and we're going to say the shortest distance from point C to line segment AE is the perpendicular through point C to AE. Well, that's line segment CE. So any other line that goes to point C and hits up to AE, like this line right here, AC, has to be longer than CE. That sentence is what we see right here, that AC is greater than CE. Now, all I really want to do is simply add the inequalities. All right, so if I add the inequalities, then I'm going to go ahead and say that BA plus AC is going to be greater than BE plus CE. Well, let's look at BE plus CE for a second. Here is BE, here is CE. And we know the segment addition postulate simply says that BE plus CE is equal to BC. So I'm just going to simply make that substitution. And when I make that substitution, I end up with BA plus AC is now greater than BC. And that's what we were trying to show, that the sum of two side lengths is greater than the third side length. And if I went ahead and just simply drew a perpendicular from B to AC, I can now show that two different line segments would be greater than the third. And if I was to drop a perpendicular from C to AB, I could still show two different line segments of this particular triangle would be greater than the third. So it would hold for any pair of line segments when compared to the third for any triangle. An isosceles triangle is a triangle with at least two congruent sides. We are going to make an isosceles triangle with exactly two congruent sides. Now look at segment PQ. Off on the side, you see segment RS, which is clearly longer than segment PQ. What I'm going to do is I'm going to drag my compass over, and notice, oh, look what happened. The width of the compass is exactly the length of RS. So I'll go over to point P, and I'll rotate an arc. And I'll go over to point Q, and I'll rotate a second arc. And what do you notice? Those two arcs intersect. So if I go ahead and allow myself to put one side of the triangle to start at the intersection and the other end of that side to go to Q, and then create a second line, and my second line would start at that point of intersection and end up at point P, I've created an isosceles triangle with exactly two congruent sides. Why is this an isosceles triangle? Well, the length of the side is exactly the radii of two congruent circles. Isosceles triangles can be acute, right, or obtuse. Take a look at triangle STQ. Now this is an acute triangle because all the angles are less than 90 degrees, and if you note the congruent marks, TQ is congruent to QS, this means it's an isosceles triangle, so it's an isosceles acute triangle. We also have a triangle PQR, and if you note these notation for perpendicular lines meeting, this means that we have a right triangle because angle Q is 90 degrees. And again, if you note the congruent marks, sides RQ and QP, well, they're congruent. So we have a right isosceles triangle. For the last triangle in this figure, we see triangle SQP. And we note a obtuse angle, angle Q. And again, note the congruent marks. So we have two congruent sides. So we have a angle that's greater than 90, angle Q, and so we have a obtuse isosceles triangle. Now, turn our attention to equilateral triangles, where we have 1, 2, 3 sides that are congruent. These triangles are also going to be isosceles triangles. Note a very important facet of this triangle is that all the angles must be less than 90 degrees. In other words, we have an acute triangle. Why is that so? Imagine increasing a single angle. So I'm going to increase this angle. Now remember, the side lengths are the same. So this side length is still the same as these two. That means that two sides would never meet up if that angle was increased. Note, if you will, also, that if you turned around and again noted the three congruent sides, but decreased an angle in length, again, all the side lengths are the same, so one side would most assuredly overhang the other. So this tells us that we have an acute triangle, and more importantly, we have an acute isosceles triangle. Why is it isosceles? Well, the formal definition of an isosceles triangle is that you have at least two congruent sides, and equilateral triangles are isosceles because they do have at least two congruent sides because they have three congruent sides.